Good afternoon and welcome to Computer Vision today. Last week we finished convolutional neural networks and looked into selected architectures. We also had the intro to the Cronus challenge last time, and I had sent out the list of all the students that signed up. Unfortunately, I received a few requests of students who still wanted to change groups, but I had informed you about the deadline and that all of this was final, so you can't unregister or change groups. And we'll continue because there was a limited number of spots, and if you unregister now, then you would have wasted someone's spot who wanted to do the challenge, and that's why there are deadlines. I will say more about the regular projects later. Sometime during the lecture or after the lecture, but we'll first finish with the content of the lecture or continue with image sequence processing. Last time we saw motion in image sequences, so for example, videos, and today we want to explore the Kalman filter. Yet for that, we first had to look into temporal models. And these temporals model that we see, they are highly generic. They can be used for features from images, and we can track those features, but we can also do this for totally different data. So they are highly generic ones. And we will use simpler data today for the examples that we will calculate, but all of this works exactly the same for multiple features from images. And we saw a few tasks for which temporal models are destined, concretely filtering, for which we want to estimate state variables that we can't observe directly, but we only have noisy observations over time. And for this, we established our mechanisms. We have states, we have observations, we have time slices, and we've introduced a transition model as well as the sensor model. And for this, we introduced Markov assumptions to keep these models bounded, and therefore what we want to compute is still feasible. Plus, we bound the time we need because we only look back a certain number of steps, and that's why Markov models were introduced. We saw the sensor model as well, and we discussed this example here in detail, and we'll use it again today to study a concrete example of a temporal model. And after that, we will then study the Kalman filter as a more concrete temporal model. Then we continued with a couple of things like the complete joint distribution, and we started looking into the filtering task. This is something we'll finish now relatively quickly, and then we see other tasks like prediction, smoothing, most likely explanation, and learning, not as detailed as filtering, and then we'll see a concrete filter, which is the Kalman filter. And we've introduced the base rule, or it's, for most of you, it's a revision who had seen it before. We need the base rule, as we saw when we, at the end of last week's lecture, started establishing this two-part process and applied the base rule here, and we've discussed these formula. What we will actually do quite often now in this course is we need to think about that, or we can see our filtered estimate. So we want to estimate our state given all the past evidence, and we can interpret this as sort of a message f from 1 to t that is propagated forward along the sequence. And it's modified by each transition and updated by each new observation. And this message can be seen as, or it will be computed by a forward function. And there are lots of different ways how this forward function can be implemented so that we get the new value from t plus 1 or from 1 to t plus 1 based on all the previous t's plus the new evidence that we are observing. And there are lots of ways how we can implement forward, and we'll see a few concrete examples this time. And we start now with this generic approach, and then we'll come later to a Kalman filter that makes more concrete assumptions so that actually computing these updates becomes easier. Remember, this is what we did last time. So we said we want to know if it rains, but we can't observe this directly, but we know, or we have an estimate. We don't know, but an estimate if it rained yesterday. So we can make an estimate if it rains tomorrow based on our estimate of today. And what we see is if the director brings in an umbrella. And we've discussed also the dependencies, which are depicted in this graphical model by this arrow. And we discussed in detail what these transition tables mean. And now we'll look into a concrete example. And first of all, I want to know from you if you're all fine with these tables here and this image. We've discussed it in detail last week and you had time for revision, but yet let us know with a thumbs up if you're okay or a thumbs down if this requires more explanations. But I'll wait a second and see. So far, there are only thumbs up. And with that, I will switch to my iPad so we can actually do a few concrete calculations. So this is just what I had shown you last time. It's the numbers in case we need to go back to the transition and sensor model. And then what I want to compute is, so say we want a filtering example. And this filtering example is we want to compute the probability distribution, so in bold, on rain on the second day after we saw umbrellas on the first and second day. So this small u is concrete evidence on days 1 and 2. We discussed that notation last time. And now, after we have seen the umbrella 2 days in a row, we want to compute what's the distribution. That's why in bold, whether it rains on day 2. For this, we need to start with an estimate on day 0. And on day 0, we actually know nothing. We have not received any evidence yet. We only have prior beliefs, whether it rains or not. And a typical common approach would be, so we assume whether it rains on day 0 is a 50-50 probability, so 0.5 and 0.5. 0.5 for it rains and 0.5 for it does not rain that day. Here, that's why it's a distribution, but it's for we have a discrete number of values, so it's not a continuous distribution, but either it rains or it does not rain. So initially 0 or 50-50. In the slides to save space, I've often used row vectors. So in the slides, this would be something written like 0, 5, 05 transpose, but this is just a row vector that we transpose. It's the same as this column vector. And this was day 0. And now on day 1, we start getting evidence. And on day 1, an umbrella appears. So U1 is true. So this is our evidence that we collect. And what we need to do now is we need to do a prediction from t equals 0 to t equals 1. So that one time step. And in a moment, we will also start plugging in the evidence. So I'll write here in blue, this will come soon. But for plugging in the evidence, we need the sensor model. But first, we need the transition model to get from 0 to 1. So t equals 0 to t equals 1. So t equals 0 to t equals 1. So what we need to compute first, which will actually not reveal much insights, but we'll get more insights once we start plugging in our evidence. So I want to compute what's the distribution of rain on day 1. Evidence will come later, and when you've seen our temporal model last week, we would first do the transition model and then start using the evidence. So what I need to compute, and this becomes easier now because I only have a discrete number of values. I have a sum, and I go through R0. And R0 is the following. So I need R1 given R0 times the prior of R0. And what I need to look into is a conditional probability distribution, which is this one here. It's a distribution, so the P is bold, and it's of R if it rains on day 1, given a concrete value of day 0, R0, and we need to multiply this with a prior in green. But the prior is up there, what we had just calculated. Well, this in green is a concrete prior value, and up here we can read this from the distribution of R0. And we need to go through in the sum all the concrete values that R0 may have, which in this case is just 0.5 and 0.5, because it's just true or false. So the update is relatively easy, and there are smart ways how we can calculate this. Remember, this transition probability in blue is from our table, the transition model up here, where we said xt given xt minus 1. And these probabilities were 0.7 and 0.3 as we discussed them last time. And we said that's the probability distribution of RT given RT minus 1. And what we put in here was the RT minus 1, which was true or false. So that's the transition model. And I can, in fact, calculate this quite easily because I can just use a vector for this now. It's 0.7 and 0.3 because I said of R1 given the concrete value of R0, and there are two concrete values of R0. We have them here and there, and the first one is 0.5. And then in the sum, I continue with the next value in R0 and the next value in R0 is also 0.5. And we still need these the probability distribution in blue. And for the negative value in R0, this would be just 0.3 and 0.7. But we discussed these tables last time. And now I want to know from you, what is the result that I'm getting here? So I have my two vectors, which are for the probability distribution, for the conditionals, and I have in green these priors here. Now, if I calculate, I take the vector, multiply it times 0.5 plus the other vector times 0.5. What is the result that I'm getting? You can try to calculate it. It's actually fairly easy, and share it with us in the chat. And it's fairly easy. It's 0.5 each. So as we've seen in the chat. So actually, we have not learned anything so far, or we don't have new insights, because all I've done is I had the initial prior, and I'm doing a transition from that prior to the next day, but I don't have any evidence yet. But I wrote before that the evidence would come soon, and we can try to plug it in now, and we can try to calculate what's the probability distribution of rain on day one, given I have seen an umbrella on day one. And from the formula we introduced before, which were these highly generic formulas for my temporal model in filtering, I can break this down to just this very simple rain and umbrella one, and I can say, well, here I can just use the base rule. You've seen before or end of last week, when we applied base rule to this temporal model for filtering. And so I can apply base rule to this element here, and eventually I can say, well, this is the probability distribution of U1 given R1 times the prior distribution of R1. So it's just base rule. But what is missing when I have now applied base rule? So I'm writing here. You can let us know in the chat what you think is missing. Because base rule requires one more thing. I can't just use this. The normalizer. Yes. But the normalizer is something I also told you we don't want to write out all the time, because it requires a lot of writing that we actually don't need. So we put this alpha in front, and the alpha here means I I have probabilities that are not normalized. Sometimes we call this evidence too, but I don't like the term evidence here, because evidence means we bring in evidence, which is our U. But the wording in probabilities is evidence for unnormalized probabilities. If I put my alpha in front, this would just denote this. And we will normalize later. And to normalize later, we'll do that at the end. What I need now is my probability of having an umbrella on day one. So this one here, given I have rain on day one. And for this, I'll go back in green to this table, which showed exactly this. I have an umbrella at time t given there is rain on time t, and the probabilities were conditioned on RT 0.9 and 0.2. And this is exactly what I can use here. So I can say 0.9 and 0.2. So the 0.9 stands for the true case, the 0.2 for the false case, because this was the true and this was false. And now I need to multiply this with my prior, and the prior I will mark in yellow, and the prior was 0.5 and 0.5, which came from the transition model. Now I need to multiply these values from these vectors element-wise. And the way I would typically denote an element-wise multiplication is this one here, but we can write this as a comment. So element-wise multiplication. And well, we multiply the 0.9 times 0.5, 0.2 times 0.5. And again, this would be alpha times 0.45 and 0.1. And I have unnormalized probabilities, so I need to normalize. And normalizing means, say I want to normalize the 0.45, I need to divide 0.45, so 0.45, I need to divide it by the sum of these two, because that's exactly how I normalize. So 0.45 gets divided by the sum of 0.5 and 0.1, and this will ultimately lead to approximately 0.818, and the 0.1 here would be normalized by dividing 0.1 by the sum of 0.5 and 0.1. And then this will be approximately 0.182. And these two values, they add up approximately to 1. I mean, it's just approximate, but here they add up to 1. So we have normalized probabilities. And in the slides, I just used row vectors because row vectors fit better in my slide deck. But we always refer to column vectors. That's why I have a transposed row vector. Are you okay with this example here, how I brought in the evidence? Maybe thumbs up or thumbs down. And it's just a consequence of our formula. And actually, this also makes sense because before we just didn't know whether it rained or whether it didn't rain. And we don't know for sure, but with these probabilities now, we've seen an umbrella. So obviously, the probability of rain outside went up a lot. And we can continue all of this if we wish, and we'll continue this now on day 2. So this was here day 1, and we'll have day 2. And on day 2, we want to go from t equals 1 to t equals 2, plus we will also have an umbrella that is true. So U2 is true. And this will also come in a moment. Like, well, what did I write before? I wrote soon, so I will also write here soon. So we will also plug in the evidence soon. But first, we need to do our transition from 1 to 2. And for that, we use the transition model. And it's quite similar to what we have done before. So P of R2 given times U1. So the new evidence will only come in a moment. And what I need to do is, it's slightly more difficult than before, because before the transition was, we had this prior here, P of R0, but this time we don't have this P of R0, but rather we have the P of R1 given U1. So this is the conditional P of R1 given U1, because I have evidence from the previous step. And what I have written here in green, or just highlighted in green, this is in fact just what I had calculated here. Well, here, the second part I've just put in green is the distribution. And here I will need the concrete value. But that's just what we have calculated in the previous step. And again, I need the transition probability distribution. And this is this time R2 given R1. But that's as before, the 0.7 and 0.3. And I go through the sum for all the values in R1. And because it's a discrete number, I can do a sum. If this was continuous, and we'll see this with the Kalman filter, if this was continuous, I would need an integral here, but it's just true or false. And this is again 0.7 and 0.3 times a value, and the other one 0.3 and 0.7. And the values we plug in here are just the values we have calculated. And this was something like 0.818, if I'm not mistaken. So exactly this one here. And the other one is my 0.182. And if I calculate this, I will get approximately something like 0.627 and 0.37. So 0.373. So what I have done is I have now done the transition from t equals 1 to t equals 2, and my probabilities are now less certain than before. Does this make sense to you or doesn't make sense? Or if it makes sense, maybe let us know. Or if you don't know why these probabilities now are less certain than before, any kinds of thoughts you may have, share them with us. So you can either turn on your mic or send a thumbs up or a thumbs down or send us in a comment, but we got a thumbs up. And so it makes sense to one student. Do you want to tell us maybe why it makes sense to you that these probabilities are now less certain? Feel free to tell us orally or in the chat. Anyone? One student says, the fact that there was an umbrella yesterday is less informative for today. And that's correct, because yesterday we had an umbrella, but now we have moved to the next day. The second evidence is not part of it yet, but it makes sort of sense that this starts to flatten out because we know less about today than we knew at the end of yesterday about yesterday. Because we don't have the new evidence yet. So this starts to smoothen. And if we kept transitioning now, if we kept doing this all the time, we would certainly, so without evidence, this would slowly converge to 50-50. But we have our evidence, the new evidence, for which there was also an umbrella. And what we can do here is we know there's an umbrella on day 2. So P of R2 given time, given U1 and U2. And in fact, what only matters here, because of our model, the U1 doesn't matter then because we have this Markov condition. We only care that we have now evidence on day 2, and we don't again go back to past evidence. That's why we made the Markov assumption, but we can calculate this. So when you go back in detail and you study these update formulas that we had, you would see, and we've discussed it last week briefly, you would see that this is U2 given R2 times the probability distribution of R2, but we don't know R2. We only knew R2 given U1. So this one here. So we would say the distribution of R2 given U1, because that's what we knew. And we can try to calculate this again. So we have an alpha Here we had the 0, 9, and 0, 2 from the distribution. We had exactly those ones here as before. And we do again an element-wise multiplication, but this time's not with the prior, but with this one here in green, which is this one. And this is then 0.627 and 0.373. And it's again element-wise multiplication. And if you do that, you would see something like alpha times 0.565 and 0.075. And that would be approximately 0.883 and 0.117. So what we see is after umbrella on the first day, the probability that there was rain on day one was 0.818. Then it became less certain by doing the transition without new evidence, and plugging in the new evidence would become even more certain because we had two umbrellas in a row. So the probability of rain increases from day one to day two because rain may persist. And we have received two umbrellas now in a row. You could continue these calculations on your own if you wish. And maybe on day three, we don't have an umbrella, and you would see that you would first do your transition and then the sensor model where there was no rain, and probably this probability here would go down quite a lot. So, did you find it helpful that we did these calculations step by step and bring the formulas from before to life? If you found this example here helpful, let us know. If you have questions, let us know too. But I think this helps a lot compared to just looking at the formulas. And everything I had shown you is also available in the slides. And we've just calculated this step by step together. And I've always tried to use the row vector, so more content fits on a slide rather than using the column vectors. But they're transpose row vectors, so we always think here in terms of column vectors. So this is filtering. We want to estimate our state by plugging in evidence, our current state that we can't observe directly. And as there is filtering, there are more tasks in temporal models, such as prediction. And prediction, this is something that someone asked last week in the lecture. Can we also look into the future? And that's prediction. With prediction, I have all my evidence of time 1 to t, but I don't want to estimate xt, so I don't want to just estimate my state at time t, but I want to look k steps into the future. So, and k must be greater than 0 that this works. So I want to compute a posterior distribution over the future state, given all the evidence up so far. So prediction can be useful when I want to evaluate possible courses of action based on their expected outcomes. And with our umbrella example, this would mean we want to compute the probability of rain sometime into the future, for example, 3 days from now, given all the observations that we have up to today, and I want to look 3 days into the future. This would be an application to our rain and umbrella example. We can again write out what this formula for prediction would look like, but I'll spare you this. You can read here the slide in case you wish. There are also more detailed algorithms like the ones we have seen here for filtering with this two-part process, but I'll skip that for now. Um, just to show you, we've just discussed briefly what prediction would be. Similarly, there are other tasks in temporal models like smoothing. And with smoothing, I want to look into the past. So again, I'm at time t and I have all my evidence from 1 to t, but now I want to estimate the distribution of my state at time k, where k is sometime in the future. So k must be greater than or equal to 0, but it must be less than t. So it's looking into the past. That's why this less here shows it's the past state. And I want to compute the posterior distribution over a past state, given all the evidence I got so far. And with smoothing, I can provide a better estimate of the states in the past than at the time what was available when we had evidence at time k. But now we have more evidence and we want to go back in time with that new evidence and maybe get a better trajectory of how something has moved. So, for example, smoothing can be interesting if we want to track an object and the object has an inaccurate position. We can sort of try to track it with filtering and see where it may be at the moment. But if I want to sort of reconstruct its trajectory and better understand how it may have moved in the past, I can go back with smoothing and get a better trajectory. And that's why it's called smoothing, because it gives me a smoother estimated trajectory. And for our rain and umbrella example, this could mean that we want to compute a probability that it rained last Wednesday, which was a few days ago, but I take into account all the observations of the umbrella that we have made up to today. Again, this can be described with something like this, but for that, I would refer you to the literature because in this course, we will largely focus on filtering then, and very soon we will get to the Kalman filter, which is a more concrete filter that makes some extra assumptions. So there's this more generic algorithm for smoothing, as well as the next task that we look at, the most likely explanation. And most likely explanation is the fourth task. So we've seen filtering, then predicting, then smoothing, and most likely explanation addresses something else. So if we have a sequence of observations, we want to find the sequence of states that would have most likely generate those observations. So far, we always thought about estimating our state, taking into account the observations. This time, we want to know, given these observations, what would be the most likely sequence of states that would have generated these observations. And what we try to compute is we have this probability distribution of, so we are at up to time t. We want to know the distribution of x from 1 to t, given all the evidence up to there. And I want to know which sequence of states from 1 to 1 to t would maximize this. So I don't put in a max operator because max operator would just mean maximizing this one here. I want to know which input from 1 to t in x would maximize this one here. And such algorithms are helpful. For example, they've been used a lot in speech recognition, where our goal is to find the most likely sequence of words given a series of sounds, and we want to do a reconstruction of bit strings, or for example, a reconstruction of bit strings transmitted over a noisy channel. If we apply this to our rain and umbrella example, we can say if the umbrella appears on each of the first 3 days and is not there on the fourth day, then the most likely explanation is that it rained on the first 3 days and did not rain on the fourth. And again, there are highly generic algorithms to describe this in temporal models. And when you come to more specific temporal models, you may come across an algorithm that is called the Viterbi algorithm. So I'm sending this here to the chat. Viterbi, Viterbi, which can be one of these algorithms to calculate the most likely explanation for a certain type of model. The last task is more of a different task because we've seen now filtering, we've done prediction, smoothing, as well as the most likely explanation. And then what we have always now relied on are these transition probabilities, or the probabilities in the transition model as well as in the sensor model. And so far, we have seen them as given. We had defined them before, or they came from somewhere. But these probabilities for the transition and the sensor model, they too can be learned from observations. And there are different ways how you can learn those probabilities. One approach is expectation maximization, or the EM algorithm. We had discussed expectation maximization a few weeks ago when we looked into clustering of data. And I told you there's the EM algorithm, which is sort of a generalization of the k-means algorithm and can be used for far more than just clustering. And the expectation maximization framework could be used for learning. But we are also not interested in this class because we could spend an entire semester just on temporal models and spend a lot of time on learning. But here we just see the transition probabilities as given. Um, Now we want to look more into filtering and look into a concrete filter, which is the Kalman filter. And the Kalman filter is an estimator for state variables, and it will differ a bit from our framework here. We will again have noisy observations. That's something we have always assumed. But this time, our variables are continuous with these very generic temporal models we wrote down so far, or then the example that we looked at. We saw the variables were discrete, and this time they can be continuous. And there are other approaches for discrete variables. So if you assume the variables were discrete, not continuous, we could model the discrete ones, for example, through a hidden Markov model, which is an HMM. Hidden Markov models were popular in the past, in particular for speech recognition. But this is now something that has largely been done with neural networks, transformer models. They are helpful. They need way more data and way more computational power. So a hidden Markov model is still, for example, much cheaper than a transformer model, but maybe limited to some extent. But sometimes for other problems, you would still pick a hidden Markov model. And transformers are not a silver bullet on neural networks because they need a lot of data. And so this was just a small note. We will focus now on a specific filter, which will become more concrete, and that's the Kalman filter. And we will assume that the variables are continuous. We will study some of the formula, and after that, we will apply it to a couple of examples, and then we will see what it is relevant for in vision. So the Kalman filter is a super famous filter. It's used for a series of measurements that we observe over time. Measurements are uncertain, so there's noise in the measurements and other inaccuracies. And we want to calculate again estimates of unknown variables. Um, and we will have multiple measurements over time. And we want to estimate a joint probability distribution over the variables for each time frame. And the variables this time, they are not concrete, they are not discrete, they are continuous. And this will change our Kalman filter a bit. Has any of you ever come across a Kalman filter before this class? If so, thumbs up or thumbs down. I'm just curious if anyone had seen the Kalman filter before. So one person has seen it. Do you want to share with us where you have seen the Kalman filter or what it was useful for in your case? You can send it to chat or turn on your mic as you wish.
Yeah, in the context of body position estimation with computer vision, but very
Okay.
briefly, like I didn't implement it or something. Just yeah.
So you've seen this as an example, or you have used a library to build this, or
But yeah, seeing it as an example would be
okay,
yeah.
okay, cool. The Kalman filter is something that was used to fly to the moon in the 60s and 70s. Now, just some astronauts flew to the moon. They're obviously now less open about the kind of methods they used, but the Kalman filter was crucial to actually fly to the moon in the US space program. The Kalman filter was proposed a few years before in various ways by various people, but most of the research goes back to Mr. Kalman and it's named after him. So Kalman filter is really cool and was used to fly to the moon. And we will now think about a bird's flight, not a spaceship for now. And if we have a bird that flies, we could specify this by 6 continuous variables at each time point. We need 3 for the position, so xt, yt, and zt, and 3 for the velocity. And the velocity here is we put this dot on top, so we use physics notation xt dot, which means the change of xt, the change of yt and zt. So the change of the coordinates x, y, and z at time t. Um, we we will model very soon our transition and sensor models, and for this we will use so-called linear Gaussian distributions. You will see in a moment what these linear Gaussian distributions are. What this means is we will have a next state xt plus 1, um, where, and that state xt plus 1 must be a linear function of the current state xt plus some Gaussian noise. And we will see that Gaussian noise is actually a condition that is quite a reasonable choice in practice when modeling things that we want to estimate. So a Kalman filter could be, for example, used for tracking, like the example that was just mentioned by one of your classmates. Um, for that, we need um, some math, and we'll develop this together step by step. So, key to everything we're doing now is the Gaussian distribution. So, Gaussian distribution. which you all have seen in your statistics course at the latest, but I'll still quickly mention it because we look at this now from one dimension and then we'll need more dimension. We describe this distribution as P of x. It's e to the power of minus x minus mu squared divided by 2 sigma squared. And what we have here is, so it's just a revision, but you will need this in a moment for multiple dimensions. And then we'll plug this into the Kalman filter. So we have a mean mu, and we have a standard deviation sigma. So sigma squared is the variance. And we describe this by e to the power of minus x minus mu squared divided by 2 times the variance. And x is a continuous variable, so x is continuous, ranging from minus infinity to plus infinity. And is this complete or is something missing here in my definition? If you think it's okay, thumbs up. If something is missing, send me a different signal. You've all seen the Gaussian distribution before at the latest in your statistics course. So if you think this definition is fine, thumbs up or thumbs down if you disagree.
Again, the normalization factor.
Yes. Why do I need a normalization? I'll ask maybe then.
Because integral wouldn't sum to 1 over infinity.
Exactly. So the integral from minus infinite to plus infinite, we want this integral to be 1. So we need to normalize this, and the normalizer is 1 divided by sigma times the square root of 2 times pi. So that's the Gaussian distribution, and I'll show you in a moment why we've done the revision. But we first quickly want to visualize it, and there are various cases. If we say, for example, the mean is 0 and the variance, so sigma squared is 1, then sometimes we refer to the standard normal distribution. Sometimes the Gaussian distribution is called the normal distribution. And you can visualize this in different ways. So, for example, the blue one, let's start with the red one. The red one, the mean is 0 and the variance is 1. If I reduce the variance, we see that this gets more sharp here. If I increase the variance, this would be sort of this orange one. We spread out the distribution more. Plus, we could also, for example, move this. So if I change the mu to -2, then the mean would be moved here to x is -2. But because we have the normalizer, the integral from minus infinite to plus infinite is always 1. And that's what we require for a probability distribution. And now we've done this for 1D. We can do this, in fact, for multiple dimensions. Who of you has seen the Gaussian distribution for multiple dimensions? If you have seen this, maybe thumbs up or thumbs down if you have never seen what I'm talking about. So, and maybe some more responses. So mostly people have not seen it. One has seen it. That's okay, but largely not. So the one we had here was in one dimension. So one dimension. And we can now introduce the multivariate Gaussian distribution, which we need in the Kalman filter. So multivariate Gaussian distribution. And this time we don't have an x as a scalar, but we have a vector x, so multiple dimensions, vector x in n dimensions. And then this multivariate one, we would write p of my vector x. And this will now look extremely complex, but I'll tell you in a moment what we have in here. We need two elements. So we have our mu, but mu is a vector. So it's the mean vector. And before we had our standard deviation, sigma or sigma squared for the variance. Now we have multiple dimensions. So we not only need variance, but we need to see something like variance between two variables. And that's something we call covariance. And covariance we can have between all the different variables. So we would have our big sigma, which we call the covariance matrix. I guess that's something you have also seen in your statistics course, how to calculate covariance. And this time, this is E. Well, he just disappeared. Well, there he is finally. E to the power of, we'll write this step by step. So I have my vector x minus the vector mu transpose times the inverse of my matrix. So I'm also putting this in bold so we know it's the matrix. And then we multiply this with x minus mu. And well, didn't look too nice. So what I have in here is vector x minus the mean vector here as well. I'll multiply this from the left and right, and from the left it's the transpose. And here I have the inverse of my covariance matrix. And I need to multiply this with a half. And then this is e to the power of this construct. And again, this needs to be, so first of all, this is not too different. I mean, it can be derived step by step with this definition, but what I had in the 1D one was x minus mu, and I had this sigma, and here I had this square, and I divided by 2 times the sigma squared. So the sigma squared I don't need. That's why I now have the covariance, and it's here an inverse, and I multiply, or before I had x minus mu squared. In this definition, I multiplied once from the right and once from the left. The left one is the transpose. Otherwise, the dimensions would not fit. And before, I had this 2 down here, and this is eventually the 2 I have here as well. Now, So it's actually quite similar, and I still need a normalizer. And the normalizer is this time the square root of 2 times pi to the power of n times I take the covariance matrix and calculate its determinant. So I have the determinant of my multivariate Gaussian distributions. It's actually not that different than for the 1D case, and we'll need this in the Kalman filter later quite a lot, this multivariate Gaussian distribution. Um, I don't know this definition by heart. I need to admit, I also need to look this up. I could probably derive it, but I would just need a little bit of time. And there's also something I don't write down too often. And we have this also in the slide deck. And you can try to visualize it for example, 2 dimensions. We could visualize this here. So we have x and y, or x1 and x2, and we can visualize this probability density function, and we see there's a normal distribution along the 1 dimension and a normal distribution along the other dimension, and this can be visualized here quite neatly. Visualizing this for more dimensions probably doesn't look great or doesn't give much insights, but here for 2D, we can do this fairly easy. Now, you're wondering, what is all of this useful for? These were some of the preliminaries, and now we'll come to our Kalman filter. So with our Kalman filter, we will simplify this a little bit now, and we will just look at the Kalman filter from one coordinate. Later, we will look at this from multiple dimensions, but we'll just keep it to a single dimension now. And here you could also imagine the computer vision use case again, because we want to estimate where our bird is. Yet the bird keeps moving. Our observations are only are noisy. Sometimes we may not see the bird exactly where it is, and the bird has an x, y, and z coordinate. Plus, we could try to estimate its velocity along the 3 coordinates. But just to keep it simple in the initial example, we just care about the x coordinate, and you could imagine this in your vision setting. You would, for example, have some feature. So we don't plug in the actual image or the actual video stream, but image like features that we would calculate from that image sequence. And these features would go in, but for now we just say it's the x coordinate. We'll simplify this a little bit. And we want to know how the x coordinate keeps evolving. Because what we know is we have an estimate of xt. It's again just an x estimate. Then with velocity x dot, the bird keeps moving along the x coordinate. And there's an interval so a certain time that passes between observations are made. And the length of the interval would be described with this symbol here. And we would see that our position update would be then xt plus the interval length is xt plus the velocity of x times the length of the interval. And we now need to include that our observations are noisy. And for that, we need Gaussian noise. There's one minor thing I before didn't mention when we introduced the Gaussian distribution. The Gaussian distribution can sometimes be referred to as an N of 2 parameters. So N for normal distribution with a mean as well as a variance. And similarly, you could come up with the normal distribution if it was in multiple dimensions, but here just for now in one dimension. N is the normal distribution with two parameters. And so if we use our linear Gaussian transition model, if I want to model this update of the estimate and add my Gaussian noise, this here reads a little bit complex, but I'll explain you this, or I'll probably write this down step by step, what this one here means. So I'll get back to the iPad. So in my bird's flight, I want to say that xt after the interval is xt plus how quickly x changes, the change of x times the interval length. And now I want to add Gaussian noise to account for uncertainty, for example, for wind variation. And that can be modeled the following. So I can say my probability where my xt plus the interval length is, so that's the parameter value, and the concrete input is my concrete one. That's why small x t plus the interval, given my value of xt, so a small x for the concrete one. So I'm highlighting in green the concrete ones and in blue the parameter values. And I need to know the change of xt. So we could assume that the change is constant, for example. Here I had sort of left out the t because I've just said the velocity, but the velocity too could be like here modeled based on change of time. And for this, I also have a concrete input. And in blue, again, the parameter value, in green, the exact input. We can try to model this as a linear Gaussian transition model. And we can say n for the normal distribution, we have xt plus the change of xt times the interval length. So this one up here. So this would be the new mean. So the mean of where we would expect the position to be, say xt plus the change of xt times the interval length. That would be the mean. And we have our sigma squared for the variance, for the uncertainty. And that would be eventually our Gaussian function. And we can try to visualize such a bird's flight as well. And for that, I'll go back to the slides.
Wouldn't that variation, like total amplitude, also depend on how long the interval was? Like,
We assume they're constant interval length for now.
okay.
Yeah. And we could make this obviously more complex, but it's just the first attempt. And the Kalman filter makes a couple of assumptions that we will later come back again to. This bird's flight could also be modeled in terms of a Bayesian network. So we've seen the Bayesian networks last time already. And our linear dynamical system could be modeled with such a structure. So we have a position xt, we have a velocity, and the position measurement, because we don't know the exact position, but rather we have a measurement Z. And this figure here is also from the Russell-Norvig book. And in our Bayesian network structure, we could say that our xt is here. The measurement depends on the position, but we don't know the position. That's what we try to estimate. We have a transition model into the future. So xt plus 1 depends on xt, but also the change at time t, so the change of x. And then our position measurement would be subject to, so at t plus 1 would be subject to xt plus 1. And that one depends on the previous position plus the previous velocity. So that's our dependencies in the Bayesian network. And welcome back from the break. And we'll put this now all together and see how the Kalman filter works and why it's actually such an interesting filter, because it comes with some very exciting properties. And so we use these linear Gaussian distributions, and they are closed under standard Bayesian network operations. That means we have a linear Gaussian distribution, we do standard Bayesian network operations that we have seen already, and we still get linear Gaussian distributions. And the filtering can be expressed, or for filtering, we need various steps. As before, when we looked at filtering in general temporal models, we had this two-step filtering calculation. And we have the distribution of xt given all the evidence up to here. So here x, this is now, so the generic one, just the single bird, the bird with the single x position that was before. But now we are back to distributions, and x is actually a vector. Later, we will very soon do calculations on a real example. Then our x will just be a single position, not a vector, just to keep it simple. But here, this bold has a purpose, and we have all the evidence, and evidence can also be multiple variables from 1 to t. And we need a transition model. And the transition model, we've seen this before with the temporal models. It's a distribution of xt plus 1 given my concrete xt. This is also linear Gaussian, and then the one-step predicted distribution would be the following. So I want to know what's the distribution of xt plus 1 given all the evidence up to there. This is actually what we have calculated before when we looked at the rain and umbrella, and we said it's the probability distribution of the transition model, so xt plus 1 given xt times xt, or times the probability distribution of xt given all the evidence. But it's continuous, and we use these linear Gaussians. That's why it's not discrete anymore. So we don't use a sum, but we use an integral for xt. So this multiplication along xt. And this is also a Gaussian distribution. Then we can also wonder how we plug in the new evidence. So I want to know the probability distribution of xt plus 1 given, so if that prediction given all the evidence up to t is Gaussian, we also need a sensor model. And the sensor model here, again, is linear Gaussian. So it's the probability distribution of e t plus 1 given the x t plus 1. That is also linear Gaussian. Then we can condition on the new evidence. So we bring in the new evidence. And what we want to calculate is the probability distribution of xt plus 1 given all the evidence from 1 to t plus 1. We, as before, use the Bayes rule because we can't calculate this directly, but what we did before with our regular temporal models. We said, well, this is the probability distribution of ET plus 1 given XT plus 1 times the probability distribution of XT plus 1 given all the evidence. And what is missing is the normalizer, so we just write an alpha here in front. Because these are Gaussian distributions, so writing out now the normalizer is really more complex than before when we had sums or very simple, just discrete variables with true or false. This time it's Gaussian distributions. So there's a real reason why we plug the alpha here rather than writing out the normalizers, because we would just waste or we would spend probably most of the writing on the normalizer. Rather, we assume we know how we can normalize and we are done. This works not just for one dimension, but for many dimensions. And eventually, we will need our multivariate Gaussian distribution. And what you can see down here for this forward message that we have looked into with temporal models. So there's a forward operator in Kalman filtering, and we will later need the multivariate Gaussian distribution. And here you see n normal distribution, but we plug in a mu vector at time 0, and we have a sigma matrix 0, which is the covariance matrix. So this is where we will ultimately need the multivariate Gaussian distribution. But in order to make this a little bit more concrete, we will follow now a demonstration that I also found in the Russell Norvig book with a one-dimensional example. So we will simplify all of this here to just a one-dimensional example where we just have a single value in x, but it's obviously a one-dimensional Gaussian distribution. And once we have done that example step by step, we'll see some advantages of the Kalman filter. And once we have seen that, we will go back to multiple dimensions. And then we're also done with the Kalman filter. So I think we are halfway through with the Kalman filter. And then I will also show you some variations of the Kalman filter and how you would actually use this in case you want to use it for your computer vision project. Every year, quite some students use Kalman filtering as part of their project. But don't worry, you don't need to implement this from scratch, but rather there is help available. Now, so Kalman filter, one-dimensional example. Kalman filter 1D example. Say just for our position X of the bird that is flying, and we want to track that bird, but we make noisy observations. So what we need is a prior distribution of where X could be initially when we start. So P of X0 is now more complex than in our umbrella and rain example, because it's not just true false, but rather it's described by a Gaussian distribution, where, for example, position X would be, and this time X0. So I need my Gaussian distribution, and this would be X0 minus mu 0. And I square this divided by sigma 0 squared. So what does this mean? I have a variance for, because I'm uncertain about the position along X. So I have a variance sigma 0 squared, and I can describe the distribution of how X0 would spread out. We'll also see a visualization later. But what we will do now will be, there will be lots of Gaussians, and we don't always want to write out a normalizer. So again, we just use an alpha for the normalization. And this will definitely make our life easier. We will always use an alpha, and each alpha will actually always mean a new normalizing constant. Obviously, not the same normalizing constant throughout these examples, but it's always the corresponding normalizing constant. So what we need next is our transition model. So what we started with is the prior distribution. And next, we need the transition model. And the transition model, we want to know how we can describe P of, or how we can calculate P of t, or P of xt plus 1 given xt. With our initial example today, we assumed that this variable was binary, so it was fairly easy to calculate. Now it's continuous. And I will model this again, as we just said before, when we looked at these update equations in the multivariate example, we said we again assume a Gaussian distribution here, and then it's e to the power of minus a half. And we say that this is xt plus 1 minus xt, and I square this difference, and I divide it by a variance along x. So there's this variance down here is actually constant throughout the example. So we assume there's always some uncertainty for our x, but we assume that this variance sigma x squared is constant. And again, this is a Gaussian function, so I put my alpha in front just to show that it needs to be normalized. This is a new alpha, obviously, but I just use alpha now throughout these examples. Always describing, we need to normalize this again. As there is a transition model, there is a sensor model. And with the sensor model, I want to know what's the probability of a measurement. The measurement is here denoted Z. The measurement Z at times t, given my xt, my state. And again, this will be modeled with a Gaussian, so it's e to the power of minus a half. Again, and I have the difference of zt minus xt, and I square the difference. And again, I have a variance sigma z squared. And this one here is an uncertainty in the measurement. So before, the sigma x squared is a measurement in my estimate, or is an uncertainty in the measurement. Sorry, I got this wrong. So this here is not in the measurement. It's an uncertainty in my state estimate. And this constant one here is an uncertainty in the measurement. This is ZT refers to the measurement. And measurements are uncertain too, because we may not see some object precisely if we see this from a computer vision perspective. Now, we have the transition model, the sensor model, and the prior distribution. And what I want to know now is I want to do a one-step prediction to get my first update equation from a few slides ago. I want to know what's P of x1. We had done this also with our temporal models for the binary example. This time it's a little bit more complex because I need to know what's P of x1 given x0 times the prior of x0. We used exactly this one or that structure when we calculated if there was rain or no rain on day 1 given we only had the prior from before. Do you remember that we had exactly such a multiplication when we had our binary example of rain and no rain? Maybe just confirm if you remember the structure with a thumbs up or thumbs down. But we had put a sum in front because we had to go through the possible values in x0. This time there is no sum, obviously, because it's a continuous variable. And so this goes from minus infinite to plus infinite along so d x0. And so it's just an integral rather than a sum. And it turns out that this one here, we will try to build it now step by step together, and we will see why the Kalman filter is something that is so interesting in the signal processing community. We also need to think about normalization. And I've noticed just even so, no student has noticed this before, but well, here actually I don't need the normalizer yet because we plug in so the normalizer will come in a moment, and then it should also be in accordance with what I had put in the slides. So the normalizer will come in a moment. I now need to look at the conditional distribution and the prior. I had written them down up here, what they look like, and I just move them down here and multiply them in here. So we have this one here, and it's e to the power of minus a half. It's x. Well, right is a bit bigger, so it's x1 minus x0 squared divided by sigma x squared. And I saw before in the break there were some questions on the project. I'll answer them later once we have finished the content of today's lecture. So it's x1 minus x0, and we have exactly this one here. So just what we had done before, essentially. And because we had this transition model defined, and there was one minor thing I was missing, because now I see it. It's obviously xt here. It's correct in the slides because it's conditioned on xt, and there was no x, but it's an xt. And here we then have conditioned this on x0. So x0 is here. It's correct in the slide, so the t was there. And then we have this prior of x0, and the prior is again e to the power of minus a half. We have the x0 minus mu0 squared divided by the variance in the initial prior, or in the prior, which is the sigma 0 squared. And since it's an integral, I need my d of x0, and I need one last piece. It's the normalizer, and this normalizer is here. We can also put it in red, so it's an alpha, because we have these two components here. We have the transition model, and we have the prior, and both of them came with, so we have the transition model here, we have the prior, they came with a normalizer. We also need a normalizer here, obviously, for the sensor model. And finally, we can move the normalizer outside the integral. So we don't need that one within the integral. Now we have this one, and we have these two exponentials. We have this one and this one here. And we can try merging this together into one exponential. So it's my normalizer, my integral from minus infinite to plus infinite. And eventually, we just have these fractions. We multiply these two exponentials. So this is actually fairly easy because I just have these two fractions. I need to, so I multiply the exponential or the e's. That means the two elements here in orange or yellow, I just merge them as well. So this is e to the power of minus a half. And this will now look a little bit ugly, but it's actually not that difficult because I have my sigma 0 squared, which came from here, times the x1 minus x0 squared. Then I have a plus. I have the sigma x squared times this one here, x0 minus mu 0 squared, and I divide this by sigma 0 squared times sigma x squared. So it's just relatively simple math. And obviously dx0. Do you all feel okay with this part here in orange? Because it's just two fractions eventually that I'm adding together. Maybe thumbs up or thumbs down, but shouldn't be that difficult. It's just two fractions that I add. So this integral looks rather complicated. And it turns out this integral can be simplified, and it can be simplified a lot. And there is a technique that is called completing the square. And completing the square is a technique that allows me to rewrite quadratics. So this is called completing the square. It allows me to rewrite quadratics in a different term. Then I can move out a term here from the integral that is in fact not needed within the integral. I have the details for this in the slides in case you're curious about the completing the square. But if I complete the square, it turns out that my p of x1 will become much simpler because p of x1 will then just be an alpha times an integral. The integral is actually gone because the integral was 1. So what I try to do is I try to move stuff out of the integral here with completing the square. And then I only have an integral left that is 1, which then is 1 times something. So that factor can just disappear. And the stuff I could move outside the integral is the one I need left. And that's in fact an e to the power of minus a half. And I would then have an x1 minus a mu 0 squared left divided by sigma 0 squared plus sigma x squared. So with this completing the square technique, I can calculate my p of x1 far easier than before. So this integral, I move some stuff out of the integral, just this one left. And what is left in the integral is just 1. And then the whole integral can disappear. I had put that in the slides, and I'll later quickly go through the slides to show you this, and you can study that for further reading. we are almost, well, we're maybe halfway done with this now. What we need to do is so we have been able now to calculate P of x1 after we had done the P of x0. We have included the transition model, but now I need also the sensor model to ultimately plug in new evidence, new measurements. And here in this notation, we use the ZT for measurements, so the evidence we plug in here. And this is then the second step, because here we have done the P of x1, and the second step of our update, so to complete the update step, what I need is P of x1 given z1. And you remember we have seen this also earlier today. We said when we had our binary example, we had P of z1 given x1 times P of x1. Who remembers this from the binary example where we had this with a sum, and that's how we plugged in the first evidence, so the first time we saw the umbrella. Anyone remembers this? That we've seen exactly the structure. We didn't call this Z, but we had an E. If so, if you remember that, thumbs up or thumbs down if you don't. Instead of Z, we just called it E, where we had the first evidence, but someone remembers. And then we had the sum, but we don't want sums, but rather we want our integrals. And we can, again, use now our Gaussians for this conditional, so the measurement given the x as well as for the prior. For the prior, we have just done that, remember. So the prior is just the one I have derived here. So we can try to continue this. So I'm just writing out the prior, which was the E of minus a half times x1 minus mu 0 squared divided by sigma 0 squared plus sigma x squared. That's just this one here. And what I need next is this probability of the measurement given my x, and that's our sensor model. So it's just this part that I need to plug in here. And so it's P of zt given xt. So this would be P of z1 given x1. And we can do this here as well. So it's E of minus a half, e to the power of minus a half. We have z1 minus x1. We square this and divide this by sigma z squared, so the variance of the measurement. Now, again, we have our fractions, and what I want to do is I want to describe this by one exponential rather than two exponentials. And if I multiply, so I would add these fractions here as before. And before we had done this technique of completing the square. And we can do this again. So step by step, dot, dot, dot. We will get to a very neat definition of P of x1 given z1. And that one I will not write down again because It's a lot of writing, but it's formatted well in the slides. So everything we have done up to here was the P of x1 given z1, and we used the base rule to have P of z1 given x1 times P of x1, and I had just written this stuff here out, hopefully without any errors in the slide on the iPad, but here it's definitely well formatted and without typos in the slides. Before, all the steps we had done together on the iPad were those ones for the prior, for the transition model, the sensor model, the P of x1, the completing the square. In case you're curious about completing the square, all the details are here in the slides in case you want to do a step on your own, but we came to P of x1, this one here, and then plugged it here where we had used the base rule. Now I said, I need to add these two fractions together to ultimately have one exponential. And if I do that and do completing the square again, so if I combine the exponents and complete the square, I get to this one here. This looks a bit ugly, and I have not written it out in detail, but I want to discuss it with you here because it's well written in the slides. I say P of x1 given z1, so my update of my state given the measurement, it's one exponential, and what I see is this is the x1 minus something squared. So this would be the mu if if you see this as a Gaussian function, because it's x1 minus something squared, and this minus something is the mu, so the mean, and I divide by the variance, so sigma squared. And this is actually why the Kalman filter is so interesting, because my mean, so my mu t plus 1 is this one here after completing the square. And the update, so my new mean can simply be computed from these variances and the measurement and the previous mean, because what I wrote up here is exactly this mean. And the new mean is eventually just dependent on the variances, which are constant, the measurement, and the previous mean, and divided by a sum of variances. And this new variance up here is eventually just a combination of the existing variances. So that I had up here. So sigma t, sigma x, sigma z, or always squared, obviously. So the variance of t, the variance of x, the variance of z, and divided again by a sum of variances. While this looks over-engineered, it leads to high performance because I can calculate the new mean and new variance just from the old mean and the old variance. And it's super easy to calculate this rather than calculating something way more complex without completing the square. So this leads to massive improvements also in the calculation speed. So I can super easily calculate the new mean and the new variance. What I have just told you here, or what I have told you, there are a few more details in the slides in case you want to read this for a revision. But this slide here, so slide 285, is probably the essence of the Kalman filter, because when I plug in new evidence, a new measurement, this update is a Gaussian function, and its mean as well as its variance just depend on the measurement and the previous mean and the variances, and the new variance depends just on the previous variances as well as the constant variances like sigma x and sigma z. And that's why Kalman filters became so popular. And here's also an example just to visualize what the Kalman filter or how it can be used. Say I want to estimate my x position So my P of x0 is, say, we have an initial mean of 0 and an initial standard deviation of 1.5. Then my distribution P of x0 looks like this. If I calculate P of x1, so I just use the transition model, what I will see is I'm just flattening out. My mean does not change in this case, but my variance, or here the standard deviation, gets bigger, and I'm just flattening out, so I'm less certain. It's an observation we also made with the rain and umbrella. And then if I plug in evidence, so my measurement is 2.5. It's again a noisy measurement because there's variance in the measurement because I also have a sigma z, but that standard deviation, so sigma z, the standard deviation is just one. I get way more certain about the true position of my P of X, or of my position X at time one, so P of X1. And what you will also notice is the mean is not at 2.5, but rather a little bit left to 2.5, um, because my initial assumption was that the x was at 0, and now I measured it at 2.5. But with the update, I don't just update it to 2.5, but I take into account my P of x1 from the transition model. So that's why this posterior distribution is shifted slightly to the left of the observation of z.1, because the mean is just that weighted average of the prediction and the observation, because the mean of that new distribution is just calculated like this, and it's a weighted mean where we also have the previous mean, which would be here 0, taken into account. So we start with the prior, we do the transition model, we flatten out, we bring in new evidence, and now I want to know from you what happens if I calculate P of x2 given P of x1. What would happen to this very confident estimate if I do the transition model to x2? I'll see if anyone wants to guess this in the chat. So what would happen to this Gaussian if I apply the transition model from x1 to x2?
I guess it would stay around the same point, but get a bit wider, but not as wide as X1. It's later estimate.
Yes,
X1's first estimate, like it will be somewhere in the middle.
it would also flatten out simply.
Yeah,
Not too much, but it
yeah.
was somewhat flattened. And if you're curious about this transition model, we had that's exactly what we did here, and you would apply this one, but we had simplified this one, so you would just use this one here. And so you have your x1, you have the previous mean, so and the normalizer, so this would just flatten out to some extent, and then you would bring in more evidence. So, this is the Kalman filter in one dimension, and obviously you can apply the Kalman filter to multiple dimensions. Like here we have our positions in X, Y, and Z, where we may see our bird. We've just done it for X. You can do it for more dimensions, and for that we need our multivariate Gaussian distribution that before we had applied, and you can plug it in there. And it turns out what we have now described with a one-dimensional Gaussian, so our transition model, our sensor model, we can describe this as well with multivariate Gaussians. And you've seen the sigma before, which was, I'll just go back if you remember, if you forgot what the sigma was for. This was the covariance matrix. So rather than using variance in the one-dimensional case, in the multivariate case, we have the covariance matrix. And this is the one we would be using here. And the only thing that gets a little bit more complex is calculating these means. And for this, we need a few helper matrices, which are called F and H. And F and sigma X, they describe the linear transition model and the transition noise variance. So this here describes the linear transition model. This describes the transition noise variance. And our H and sigma Z, they are the corresponding matrices for the sensor model. So H to plug in the sensor or do the updates with the sensor values, and sigma Z would be the noise in the measurement. And as we've seen before, how our mu and sigma squared could be very easily calculated as these weighted means from before. In the multivariate case, we can also neatly calculate our vector sigma t plus 1 as well as our covariance matrix as it evolves, which is large sigma t plus 1. I'm not writing this out here in detail, and I'm not expecting you to remember this. I too don't remember the exact details, but it can be derived, and I've seen how it gets derived. The beauty is only, or what you need to remember, as for the one-dimensional case, where we could describe the updates when we plug in new evidence, we could describe the mean very neatly, as well as the variance. This again works in the multivariate case very neatly, simply through an addition of vector matrix multiplications. The exact details don't matter, but again, this is super efficient, and because we've taken advantage of completing the square and it can be run very efficiently. There are a few more explanations in how you can interpret this here. In case you want to do some further readings about the Kalman filter, there are a couple of slides here for the general case, but I don't expect you to know this for the projects. You can use the Kalman filter for your projects, and don't be scared about the Kalman filter because you can use a library. There are lots of libraries for for the Kalman filter. So you don't need to implement this here from scratch, but rather you can use a library. And every year we have students for their projects using the Kalman filter, for example, to track cars. Some they played billiard and they wanted to track something in billiard or whatever. So or track other objects, track cars, whatever. So there are lots of opportunities to use the Kalman filter. That's why we've discussed it today, so you know what it is. But obviously, you can use a library. You need to calibrate the Kalman filter, in particular with respect to the covariances, which is probably not that easy and takes a little bit, and it's a bit of trial and error. But you don't need to implement the Kalman filter from scratch. And in your project presentation, I would not quiz you on some deep details of the Kalman filter, but rather you can apply it to your project. Um, we've earlier today talked about tasks in temporal models like filtering and smoothing. And so the Kalman filter is shown in this figure. So what we see are, say, we want to track some object in the XY plane. So we have two dimensions, X and Y. And in blue, we have the true location, which is down here, and we observe it in various locations. And the observations are these red stars. And with Kalman filtering, we are unable to see the object directly, but rather we make observations, which are noisy, and we try to filter and estimate where the object would actually be. And these are the green dots or the green crosses. So I can zoom in and show you this. So blue means the true location. The observations are in red. but the observations are noisy too, and that's why we estimate something, which is the filtered one in green. And here we would filter the trajectory of how this object moved from our observations. And that's filtering. We don't know the exact location. We've obviously put here in the plot the exact location, but over time we get better and better. And we've also talked today about smoothing, which is another task in temporal models, where we go back in time with the extra evidence we have collected and we try to update our trajectory. And this would be a Kalman smoothing. So you can do Kalman filtering, you can do Kalman smoothing. And here at the end, we would take all our evidence up to here and go back in time and try to update our estimates, so the smooth ones, and we see the smooth trajectory in green is certainly smoothed compared to the green trajectory here, which we try to filter from our noisier observations, and we compare it to the true trajectory. We certainly get quite a difference when we have this extra evidence and go back in time trying to smooth or reconstruct the trajectory. Maybe just let us know with a reaction whether you see the difference between filtering and smoothing here. We looked at the equations today, or the formula today, and here you have a visualization of what's actually the difference between filtering and smoothing. So maybe just a thumbs up or thumbs down whether you see the difference between filtering and smoothing. It's two different things. They make different assumptions, and you can obviously only do smoothing once you have extra evidence, but it can help us to get a better estimate of the trajectory. And this is the two-dimensional case. So we have our variables x and covariance and all of that. And what we have here is not just x and y, but also the speed of x and y, so how much x and y changes. But we have visualized this in the xy plane, but the change of x and change of y was also considered here. So Kalman filters have become super popular. They cannot just be used in tracking of motion. Kalman filters can be used for any system that is characterized by continuous state variables and noisy measurements. Kalman filters have been used for far more than tracking motion. They have been used for systems like pulp mills, chemical plants, nuclear reactors, plant ecosystems, economies, and lots of other stuff. We can use them in vision for tracking, but they're so generic, we can use them for so much other stuff. But maybe some of you want to use a Kalman filter for tracking of motion in your projects. I guess you have all the tools available now. The Kalman filter, as I said, is something that was proposed before the moon landings. And obviously, over the years, lots of improvements have been published because the Kalman filter makes strong assumptions like these linear Gaussian transitions that we have in the transition or the linear Gaussians that we have in the transition and sensor models. These are strong assumptions. If we have nonlinear movements, there are other systems that were proposed over the years, like the EKF, the extended Kalman filter. It includes nonlinearities in the systems that we model. If you have multiple objects that you try to track, a Kalman filter will not work because it's aimed at a single model or at a single object. And if you have, say, you have a bird here and you have a tree here, then the bird will ultimately fly to the left or right of the tree. And with a single Kalman filter, that is quite difficult to keep track of. So sometimes you have a switching Kalman filter. You would have one Kalman filter here as well as one there. And so you would have two Kalman filters and you would switch between them. So they would run in parallel. and each has a different model of the system. So that's something, if you have multiple objects, not just one object, you need a different model as well. So there are many, many suggestions or proposals of how to improve the Kalman filter. Are there any students in the computer vision course who also take the AI project this term with me? If so, thumbs up. I've seen a couple of names, I guess, maybe from exchange students. So if you do the AI project as well, I know it's 1 year ahead for the regular students, but some students take it. Some may be exchange students. In one of the AI projects that we do with industry, we also try to do sensor correlation and sensor fusion with neural networks this term, which would be going beyond the limitations of a Kalman filter. So it's something we're experimenting this year with in the AI project. Yet the Kalman filter has a very solid foundation and it runs super fast. While with a neural network, we need a lot of training data, we need a lot of computing power, possibly, but it's something we're exploring in one of the AI projects this term. But the Kalman filter is proven to work well on so many different use cases. We don't need, it's not a system that we would train here, but rather we need to model the variance or the covariance and a couple of other things. But this runs super fast without any sophisticated GPUs, and it works for a huge number of different problems. And that's why I still teach the Kalman filter, because it's still used in a lot of applications. There are limitations, there are improvements. We are studying improvements too in the AI project, but it's still a very solid foundation. There are also videos that explain how the Kalman filter works in case you want to watch these videos. When I taught this course for the first time 6 years ago, I had only put in a few videos and said, oh, the Kalman filter is important, watch the videos, because in the first year I didn't have time to prepare the Kalman filter in detail and I was running the course for the first time. But then as of 2021, I've been talking about the Kalman filter. I think this year I'm talking in greater detail about it than last year, especially I think with some of these calculations here, I had often referred to the slides or walked through the slides. This time I try to write them down and study them with you in greater detail. Hope there was no errors in my writing, but you definitely have the ground truth here in the slides. Now we'll come to another vision example, and it's purely a vision example. So Kalman filter can be used for vision, can be used for other stuff. There are now two minor chapters for today, and after that, I will be talking about the projects because there were some questions, and I'm aware of your questions. So then there is a generic problem in computer vision that is the correspondence problem. And actually, we had come across something like the correspondence problem before. And I want to formalize this now. And then we see how we can address the correspondence problem. So the correspondence problem is the problem of ascertaining which parts of an image correspond to which parts of an image. But so that's something you may have actually quite often. For example, I don't know if you try to glue images together, make a panorama pic. But to me, the correspondence problems also means that where these differences are due to the movement of the camera and the elapse of time and or movement of objects in the photos. So what does that mean? Correspondence is a building block in many applications. We will very soon see what the optical flow is. With the optical flow, we'll have a framework to determine, we have two images that are subsequent in time, and we want to determine what has moved from that one image to the next image. So with the optical flow, we address the correspondence problem. But there are um, other applications of correspondence. For example, dense stereo vision. So stereo vision means we have a camera pair or multiple cameras that look at the same scene from different positions and different angles. With that, we could do 3D reconstruction. There is cross-scene correspondence, so in which images are from different scenes entirely, and we try maybe to have a correspondence there from one scene to the other one. There's also structure from motion or visual SLAM. So SLAM stands for simultaneous localization and mapping. That's something that is of interest to autonomous robots. So you have an autonomous robot, and it may have a map of the world in which it works, like in a factory, but in other settings, you don't have a map. And if you have a map, you don't need SLAM because all you need then is localization. So the robot needs to determine where it is in a specific map, assuming the environment does not change, like a factory, for example. But if we apply a robot in the real world, it cannot directly locate where it is because it doesn't know its map. So it needs to simultaneously build a map as well as locate where in that map of this growing world it actually is. And visual SLAM means we use a camera for simultaneous localization and mapping. And that would also be an application of correspondence. And we will look into one of these algorithms now in detail. It's called optical flow. And in optical flow, imagine we have an image, so a function I of x and t, sorry, x and y at time t, and one image later, so in an image sequence, I is then a function of x and y in the next time step. And what we could notice is that maybe some objects or some parts, they move within the image sequence. Say something moves from the left to right, something moves from top to bottom, from left to its upper right, something like this. And we want to see where objects keep moving in an image. So we will care about relative motion between the observer and the scene. And we will have an example here, for example. What we see here is this is just before a football match is beginning, and we have the football players walk in, and there's most motion among them because they come in to the football field. And they would be moving most, but we would also see a little bit of motion in other parts of the image. For example, here among the fans, because they may be moving their head. Maybe a fan is standing up or sitting down. Yet most motion would be in that part of the image from one image to another image, say maybe half a second later or 100 seconds later, 100 milliseconds later, whatever. And we want to see now how we can actually calculate such movements from one image to the next image. And this is something that I will also develop with you on the whiteboard. So, the optical flow allows us to describe this. The optical flow makes a couple of assumptions. I have written them in the slides. I will just quickly mention them here with bullet points. There are more details written in the slides. So the optical flow makes a couple of assumptions. One is brightness constancy. Brightness constancy means we have one point in a pixel image, and that exact point, so that the the point of a specific object looks exactly the same in every frame. So the illumination or the brightness of that pixel does not change. In reality, it will probably change because illumination keeps changing slowly, but we ignore that, at least in the initial model. The next assumption is small movements, so small motion, so that points do not move very far from one image to the next one. And because we have regular updates and we don't assume any big motions, and we also assume spatial coherence. And spatial coherence is something we have also actually noticed already when we looked at image sequences. We assume that points move approximately like their neighbors. Obviously, that doesn't always fully work if the neighborhood is bigger, but in the immediate neighborhood, probably those points don't move very different to their neighbors. And this is the optical flow, and we can try to express this now. And everything we have just assumed here, we can try to put into formula. So we can say the intensity, so I of x, y, and t. You've seen this approach already when we looked at the Harris corner detector, where we said we have a function I, so the intensity of a pixel at x, y, and now we just add a third parameter at time t. We assume that this is equal to a small change from typically one image frame to the next one, so small change in time. We would assume that this is the same as if x, y, and t change. Concretely, we change x by adding delta x on it. So we add a small change on x on top. We add a small change on y on top. And we have a change of time as we progress from one image to the next one. And this is the brightness constancy that we had just assumed. This is actually reflected by exactly that, because as time slowly progresses, or just from one to the next image, we assume that maybe a pixel moves a little bit because there is some motion, so it moves along x and y, but the brightness does not change. Do you agree all with this definition, that this is the way how we could assume brightness constancy? Maybe thumbs up if this makes sense to you, or thumbs down if that does not make sense. This is the change of time. And we said these points move a little bit along x and y, but their intensity does not change. So I see agreement, because this is the intensity function. Who of you remembers Taylor expansion? We did that a few weeks ago. So do you remember when we did Taylor expansion? I want some more responses here, some thumbs up or thumbs down from Taylor expansion. So we did Taylor expansion or Taylor series. So I see quite a few responses. That's something we also used in the Harris corner detector. And we can use this concept again here now to apply a Taylor expansion to this one here. So where we said we move along x and y with our point as time progresses. And if I have a Taylor expansion of that term, it turns out I can change this. It's actually quite similar to what we did with the Harris corner detector. So this is x, y, and t. So I of this, plus we have our delta x and its change of the intensity. So we have the change of the intensity along x times delta x, the intensity function, plus we have the change of the intensity along y times delta y, plus we have the change of the intensity along the time times delta the time, so the change of time, plus dot dot dot, which are the higher order terms. Higher order terms. That's exactly what we did. The same concept here. What we did when we built a Harris corner detector, just without time, but this time we include time because we have an image sequence. That means from our original equation, so I'll use this now in orange, we said the intensity of xy at t is the same as this one here, but to the right term we have applied a Taylor expansion, and that one is all of this. And we will ignore the higher order terms, and we will, so we just kick out the higher order terms, so we ignore them because there could be infinitely many ones possibly, so we just ignore them. And then we have the intensity of this is the same as the intensity of this plus something, so plus these three terms here. That means on the left and right, we can just kick out of the equation the intensity of xyt. That means we only have here in green these three terms left. So I would write this out again for you. So the change of the intensity along x times delta x plus the change of the intensity along y times delta y plus the change of the intensity along the time times delta t is 0 because we have ignored the higher order terms. And now I will divide by delta t. That means if I divide by delta t, well, I'll probably write divide by delta t in red. So we divide by delta t. So we would each component of the sum divide by delta t. And then these two here cancel out. So this would result in the following. So we have the change of the intensity along x, and this previous term, delta x times delta t, we would just call this Vx. You can do this also in blue. So Vx would mean the velocity or the optical flow of the intensity plus from above the change of the intensity along y plus the change of the intensity along t, and the delta y times delta t is Vy. So Vx and Vy are the x and y components of the optical flow of the image I. So I'll write this down. I of xyt. So these would be the components of the velocity of I of x, y, and t, and the others are the partial derivatives of the image at x, y, and t in the corresponding directions. And we can further write this. So these partial derivatives, we can write them out again. So we can write Ix is now for the partial derivative, Iy, and we have these V's, Vx and Vy, sum them together. and we can subtract the last one. So we can say this is minus I, well, we use just an I here, I t. So this equation here is key to the optical flow because the components of the velocity, that velocity can also be called optical flow. So slash optical flow. And this equation here can be rewritten again. We can say this is nabla I, which means just a change of I. So X, well, I use the color as before, I guess. Then it becomes more intuitive. Green, nabla I times V, and V is a vector. And this would be minus IT. So this is an equation, but the only problem is this equation is in two unknowns, and we are unable to solve this equation. So we are unable to solve this because we can't solve it at this. And this is called the aperture problem. And the aperture problem is a key issue of optical flow algorithms. And we need to find the optical flow, another set of equations. So we need to make some additional constraints on the movements. If we don't do that, we're unable to solve this. Now, what is the aperture problem? We will try to visualize it. And for that, I will go to the slides. So in PowerPoint slides created from LaTeX, I'm unable to visualize movements or animations, but we can go to the aperture problem, which is available in, for example, Wikipedia. And I'll show you this now, and you'll see what the aperture problem means. We will screen share this one. We can zoom a bit in. Oh. So we have a bigger object behind this hole. So this is the aperture problem. I'll quickly explain what it means. We have a bigger object there moving behind this hole, but I can only have the small hole and look a little bit in here. This object could be moving in many directions. It looks like the object is moving down to the right, but it could be moving in other directions. That object could only be moving down. It could only move to the right. I don't know, and I'm unable to determine this unless we can see the whole object or we make some constraints or some assumption. From just this hole, I'm unable to determine how the object is moving. Could be moving in many directions. Maybe just let us know if you understood that problem from this visualization. But seems fine. And that's why the optical flow, as we have described it here, we are unable to get much out of it unless we make further conditions. And for that, there's a very nice website that visualizes this. And I had put the URL in here because there are lots of different optical flow methods. Unfortunately, this is the demo effect. The URL I have referred to, it worked a while back. The website is not available anymore to show us concrete implementations of optical flow methods. I didn't check this earlier today. But I will send you a different reference and update the slides, and I will send you this today after today's lecture because this website was actually really cool and provided lots of different implementations of different optical flow methods. We could open it. I'll quickly try this with archive.org and see if that one provides us with anything, but archive.org also doesn't have it stored. So I'll find a different reference and share this later and then update the slides. So when I checked it a few weeks back, that website still existed, but I'll also refer you to some books or some other pages where there are concrete or different optical flow methods implemented that make some extra constraints. Because that was anyway supposed to be your further reading, and I will update this and share it later with you. Are there any questions so far about image sequence processing? If so, maybe just raise your hand and I'll wait for you. Otherwise, I will move to the project part. Because there were some questions about the project and I've seen your questions. So what we have done in this course so far is we have started last week we had the kickoff, or not a kickoff, the pitch of the Cronus Challenge. And we have now all the students assigned to the Cronus Challenge, and all the groups have been formed, and I had sent you the list. After that, some students still asked for further changes. They wanted to change group or project, so that's not possible. If you're on the Cronus challenge list, you have to do this. You can't do a regular project then because you would be taking someone's spot, and there was a deadline yesterday for that. Now, the students doing the Cronus challenge, we will have the kickoff next week. So all the students on that list I had sent around yesterday. And so next week there will not be any lecture here online, but all the students doing the Cronus challenge, they will meet us for the kickoff on site. And I'll probably quickly share my browser for that. And this list I had shared with you yesterday. Next week, Thursday, April the 23rd, we will meet at 2 p.m. in Vorlesungssaal Veilchengasse 2. So that's in the city center. It's off campus, but I have put the Google Map URL here. And that kickoff needs to be attended by everyone who is signed up for the Cronus Challenge. Be punctual. We have, I think, 115 students who signed up for this. So the kickoff will be lots of fun. And what you need in the meantime is create a Kaggle account, and all the information of how to join the challenge will then be presented to you together with the Cronus engineers. So next week, we don't meet online. And for those of you doing a regular project, so those who have not signed up for the Cronus challenge, you need to be thinking now about your project. It can be any project related to computer vision, and you need to submit your project very briefly via iLearn as of today. So the portal will open now in a few minutes, and you need to submit until until next week, Thursday, until the end of next week, Thursday. So you have 1 week. You need to make a submission, and in that submission, basically, you just need to write your title, what you want to do. If you write a quick description, that's okay too, but your title is sufficient. Plus, in the submission, you put all the names and student IDs of the students, and one submission per group, please. And it's really 2 to 3 students, not one student, not four. You have to do 2 to 3 students, and one submission per group through this portal. And this portal will be here. It will open very soon in a couple of minutes. And this only concerns the students doing a regular project. If you're part of the Cronus Challenge, you don't need to submit anything. And then in next week, Thursday is the submission deadline. So end of next week, possibly next week, Friday, I will compile a list of all the projects that you have submitted. Remember, one submission per group is sufficient. And I will then provide you with the list, probably next week, Friday. And in 2 weeks from now, so April 30, we will meet online here in this online session. And every group will briefly present their proposal. So, what you should prepare is 1 or 2 slides telling us what you want to do, because through the submission, you only need to submit your title, but you would do a very quick presentation, 1 or 2 minutes in 1 or 2 slides. So not more, because we'll have a lot of groups that want to present. And you would just tell us briefly what you want to do and how, ideally. So if you have a quick structure in your presentation, that would be very helpful for methods, whatever. You may have questions, and I'll be happy to answer them. And then I would approve your project, or I would give you some recommendations, or would ask you to make some changes in case there is something major that wouldn't fit. And every year there are some groups that want to do very similar work. So you would see other groups who also want to work on a related topic. So you can synchronize with them and somehow make sure the work you would do is different. Because some groups every year, I don't know, want to do, now, I'm not revealing which topics, but every year there are some topics that quite a few groups want to do. And that's fine, but you should see at least what the others want to do. So you do something somewhat different. That's our agenda. I've seen there are questions. I will respond to them very soon. So that's the proposal presentations in 2 weeks. And in 3 weeks, we'll have another lecture here. In 3 weeks' time, we will look into the last chapter, selected topics. We will probably not discuss all of these selected topics. Every year, some projects are on self-supervised learning and vision transformers. So maybe this year we will not cover this in the lecture, but I may be talking a bit about biases in data sets and uncertainty in learning. And this is important for everyone. Also, if you have started your project or you're part of the Cronus Challenge, the stuff we're discussing here in selected topics is super important, and it will probably help you to build better projects. For example, if you know how to address uncertainty in learning or how to reduce biases in data sets, this would probably mean to better results and therefore also to, in the Cronus challenge, maybe to a better scoring of your group, as well as for your other projects, better results. So that's what we will do in 2 weeks, in 3 weeks, and a few more notes when we have the final project presentations. So the final project presentations, they take place in June. I had communicated the dates to you before. If you do the Cronus Challenge, all these presentations will be on campus on June the 27th. And you need to block the whole day, at least from 8 a.m. to 8 p.m., possibly longer, because it's 41 groups and there will be lots of questions. We need to do the ranking, so block the whole day, because Cronus will also award the prizes, so you need to be there at the end. And for all the other projects, they will be presented on June 20, 21, or 28th. You are unable to pick a specific day. I will assign a day based on how I consider this necessary, based on topics or whatever, or that the presentation spread out during those 3 days. And you need to attend that one day on which you're presenting. So if you do the Cronus Challenge, you need to attend all June 27. If you present on one of the other days, you need to attend to all the presentations of that day. If you have a robot for your project, you need to return the robot sometime end of July or early July. I'll say more about this later in the course. I have talked about the marking schemes. There's a marking scheme for a regular project, for the Cronus Challenge. It's a little bit different. And there are unfortunately a few sad things that I keep observing every year. For example, some students try to pick a specific date and time when to present. Please don't send any emails of that sort. You can't pick the date. And you need to attend all the presentations of the day on your presentation. So we have these 4 days, and you need to exactly attend one of these days, and you need to attend all of them. I don't care about any excuses, like every year a lot of grandmas die, or buses were late, or someone lives in Munich. Honestly, I don't care. And you need to attend on the day, on site, all the presentations. The Q&A may also cover everything discussed in the lecture. So you should be familiar with the content. So please do not try to negotiate the scheduling of presentations. There are no online options, and you need to attend all presentations on the day of your presentation, which means you need to be there at 8 because we are starting at 8. If you're late, you will not be allowed to present, and you fail the course, and you need to wait 1 year until we offer that course again. And you're also not leaving early on that day because you need to attend all the other presentations. If you miss the other presentations, because we have some students in the past, they walk in only for their presentation and then they leave. So they come late, they leave early. Like this, we don't have a discussion. And actually, I want that we all discuss all the projects together. So you can't leave early. And the Q&A session may cover everything of the lecture. I will not specifically quiz you on details of the lecture, but yet you should be familiar with what the lecture was about. And I also want to see that you know what you have actually built rather than just gluing some APIs together. Um, I got a few questions here. Um, where do you get the data sets from? For the Cronus challenge, well, this will be provided by Cronus through Kaggle. For any other project, you can pick any data set you want. There are data sets on Hugging Face, on Kaggle. You can use a search engine specific to data sets and so forth. So you can create your own data set. You're free in doing all of that, and feel free to read also these books to get a better background. And there's again a question about the minimum number of people. I've said this before. It's you can only do teams of 2 to 3 people. You can't do a project alone. We don't have groups of 4 students, so you need to find someone else to work together with. And we have also written this here, groups of 2 to 3 students, and no exceptions here. Um, yeah, and there was another question how you choose the topic of your project. Any project related to computer vision, I'm more than happy with. And that's why you do the proposal presentation in 2 weeks. So we can talk about your proposal and see if any corrections need to be made. Meanwhile, I got some emails here about the computer vision course, so just checking them in parallel if there's anything I still need to answer. Um, and someone wants to know if he can also build his own convolutional neural network or whatever. Yes. So some people, they use a pre-trained model, they fine-tune it, they integrate it in some bigger apps. Some, they build a neural network from scratch. You can use OpenCV, you can use other libraries, but the project should be challenging and not just downloading a pre-trained model, put in 2 images, and then present the results. That would not be adequate for the work that you're expected to do until the remainder of the term, because we still got 2 months from now until the project presentations. Um, any other questions? If there is, we want to hear if you can use AI for writing code or planning the project. Yes, but you still need to understand what you're doing. You may be quizzed on the code and what you have done. So you really need to know what you're doing. And you choose the topic, and you can get any data you wish from Kaggle or other websites or search engines for data sets. This is really up to you. Some create their own data sets every year. So it's a very free choice, and we have a lot of very interesting projects every year and lots of creativity. There was one question here about one of the Cronus groups has 4 members. That's an exception because in that group there were some strange problems. One person had signed up and didn't leave, or I don't know. So there was exceptionally one group with 4 members, but they had communicated this to me, and there was really no other way to fix this because someone signed up for a group that he should have not signed up for a last minute. But that's a one-time exception. For the regular projects that you're doing. It's groups of 2 to 3 students. Um, yeah. So you can use synthetic data sets, you can use real data sets, academic ones, industrial ones. Just come up with an interesting project and you will have your proposal presentation in 2 weeks. Remember, the proposal presentation should be just 1 or 2 minutes, 1 or 2 slides, because we may have, I don't know, like 50 or 60 groups that want to present a proposal. And if your proposal takes 10 minutes, we won't be able to finish this within the 3-hour slot. So if there are no further questions, we are done for today. I look forward to seeing the students working with Cronus next week on site, all the other ones online in 2 weeks for the proposal presentations, and then everyone again in 3 weeks for the last lecture for the selected topics. Sometime in May, there may be a guest lecture or something of a company, but this is still to be sorted out. If that takes place, I'll let you know. Have a good afternoon. Bye bye.